Good afternoon, all. Today we have the fourth lecture in the series on statistics in research and research methodology. Before proceeding to the day's lecture, we will have a recap of the previous three classes. Initially, in the first class, we had discussed regarding the roles of statistics in both daily life as well as research. Then went ahead for the definition of different physical quantities, the factors affecting the measurement of various quantities, which include measuring tools, the personnel involved in the measurements, and the environment during the measurement of these physical quantities. Further, we had discussed how to present the data obtained during your research, how to appropriately present it so that the other person can appreciate your data and get the useful information. Then in the same class, we had discussed regarding the accuracy and precision of measurements. In the second class, we discussed regarding significant figures, place values, and rounding off, and the rules pertaining to each of these parameters. In the third class, we had discussed the error propagation rules for various mathematical operations and applied these rules for such operations in addition to the recapitulation of significant figures and rounding of rules. A few exercises were given for you to do at home. Hope all of you have attempted those ones. The answers to those are given in this and the next slide. The question numbers are given, the respective slides you can refer back to and check with your answers to. Those given in purple font colors in those tables are the answers to the questions, and the blue ones are the question. So the number of significant figures might be well true for all of you by now. So I will not discuss these things. You all can have a cross check with your answers. Okay. If at all any clarification is required, we will keep it aside till the end of the lecture. Then the rounding of the expressions. Essentially, the idea is to express all these expressions in scientific notation and come up with a required number of significant figures. Here, up to 4 significant figures, all the results are rounded up. Wherever required to represent properly, scientific notations should be adopted. Okay. Then in the third question, to find out which quantity to be measured, what is the propagated uncertainty during the calculation of radius of a circle via the measurement of the length of the chord and distance between the perimeter and the length of the chord. The corresponding equation was also given. All of you might have tried, I hope. The answer is derived by propagating the errors associated with each of these factors, and in the seen in the expression here, multiplication operation in addition to addition and division. These are the things you have to take care of to arrive at the answers. All of you may please check with yours first. The answers are shown in purple color. These are the answers to the questions given in the last slide of lecture 3, wherein the uncertainty in the function x as a function of u and v parameters are given. All the 5 answers are given on the rightmost column of the respective tables. And in the second question, while calculating the resistance of a cylindrical conductor, which parameter, either the radius of the conductor or the length of the conductor, which should be measured more precisely? The answer to the question is the radius should be measured more precisely, because the factor involves a square term of the radius, whereas it is linearly dependent on the length. So definitely, since the radius factor is considered twice, the better precision should be acquired during the radius measurement. And the relative uncertainty, as propagated, you can see that it should be half the relative uncertainty in L. So if you have a choice between 2 measuring tools for measuring radius and length, the one having better precision, you opt for the measurement of radius. So that way you can judiciously come out with better precise results of the resistance of a particular cylinder. So with all the tools in hand, which one to use for a particular occasion. So that judgment can be made via addressing the problems by just having an estimate of the propagated uncertainty as we discussed in the previous class. All of you might have followed and you might have tried your best to arrive at these answers. And please have a cross check. Third question is regarding the refractive index of a medium via the Snell's law. The answer along with the uncertainty is given. Refractive index being a ratiometric quantity does not have a unit. Okay. Now today's discussion is regarding the errors in measurements and the type of measurements and how we can, what are the sources of such errors, how we can tackle those errors. Those things we will discuss in detail in today's class. Okay. So generally, when we start any measurement, if we have got a large number of data, what we do is we take out particular portions of the entire data. We call those particular portion as sampling. So while doing the sampling, while taking out representative portions of the entire data, you have to be very careful while taking out the representative portion. That is the sampling. Sampling is the most vulnerable part during the errors in the measurements. So sampling strategy should be appropriate so that you can minimize the errors associated with that. Sampling size is also important. We will discuss those things in detail in the coming classes. So if you have got a large number of data available from among us, like a population, we call the large number of data as population, and the portion which we analyze, which we do subject for research, that we call as sample. Okay. So what we calculate is essentially nothing but the sample mean and sample standard deviation. And we extrapolate these parameters, these properties to that of the entire data, that is the population. Population is a superset, you can say, and sample is the subset of that. Several samples accumulate together and will go to represent the population. So if you are sampling, if your representation is not proper, you may not be able to get the exact picture regarding the population. It is not that you take only one sample at a sample during the entire measurement. You will be having several such aliquots of the entire population, which we call as n number of samples. When we have n number of samples, you take repeated measurement of such n samples, arrive at the mean of that measurements. Then since these n number quantities are having different characteristics, slightly different characteristics, you will see that there is a spread in the measured data. So that spread normally we represent in terms of standard deviation. The expression is given in the yellow background with black font color, the mean and the sample standard deviation. Since we take a representative portion of the entire thing, we call it as the sample parameters, sample quantities. Generally, English alphabets or lowercase alphabets, English alphabets, if sample quantities are represented in English alphabets, both population and sample quantities. Lowercase alphabets are used for sample quantity parameters expression and uppercase alphabets for population. If at all there is a flexibility, what we normally do is sample parameters are expressed in English alphabets and population parameters are represented in terms of Greek alphabets. Okay. So sample mean is represented as X bar, whereas population mean is represented as mu, and sample standard deviation is given a symbol of S, lowercase s in English, and population standard deviation is given a symbol sigma. And the corresponding equations are given here. These things are well known to all of you, so we go ahead. Okay. So if we measure a quantity repeatedly, provided this is a continuous variable, we had discussed two types of parameters, discrete and continuous variables. Continuous variables during the measurement, there is like if you do repeated measurements, most of the time it is having the least probability that you land up in the same value in repeated measurements. Slight variations will be there. That is why if you plot the number of observations versus the quantity number, numerical value, you will see that there is a spread, there is a distribution of the measured values. So normally it follows a random distribution, which generally follows the Gaussian function. So we call it as a Gaussian distribution or a random distribution or a natural distribution. Okay. So it is not a singular value for essentially for continuous variables. Continuous variables measurements, you will see that there is a spread in the measured quantities. What we normally do is we take the probability of occurrence of such data, repeatability of that measurement, and then take the mean value of the bell-shaped curve, which is representing the Gaussian function. So that mean value is given by the equation sigma xi by n, and the standard deviation gives the width of the spread of the bell-shaped curve. So there is another terminology called measure of central tendency and measure of dispersion. So mean is a measure of central tendency, standard deviation is a measure of dispersion. How long is the base of that bell-shaped curve? Okay. So essentially all what we do is try to understand what are the probable sources of errors, what are the probable causes of committing mistake while acquiring data, while doing the measurements. So that process is called the error analysis. It is nothing but the study of uncertainties or the random variations while carrying out measurements. So you sit down and try to analyze the data. If post acquisition of the data, you try to analyze the data and try to locate where from the mistakes or errors have occurred. Then what will happen is that in future, you can plan your experiments accordingly so that the same mistakes are not committed again and again. So error analysis will help you to understand what is the error, what is the measure, what is the magnitude of the experimental error, what are the probable sources of such errors, what are the different types of errors, whether we can address it, we can reduce it, we can almost make it nil. So these things will be deciphered from the error analysis. Further, in future, if you want to plan some experiment based on these building blocks, this error analysis will help you out to see that whichever step is having the largest quantity, largest contribution of error, you can address that step with careful precautions so that you come up with useful, meaningful, precise data. So error analysis will help you to design an experimental method so that you can save time during your research. Also, the data will be more reliable so that you get better precise data with the limited or stipulated time. So that way, every time when you do a new measurement, try to follow the literature if at all it is available. If not, plan the experiment in advance, try to address the vulnerable or the weaker points, weaker steps in your measurements, which are probable to occur, so that you can save time, energy, instrument, as well as you can acquire your doctoral degree faster. So measurement errors are generally defined in two ways. One is called the absolute error, another one is the relative error. These things are familiar to most of us. So these parts we will go a bit fast. Okay. Absolute error is nothing but the difference between the measured value and the actual value. Normally, this is a representation, measured value minus actual value. So it will tell you how higher or how lower or how positive, how negative your value with respect to the true value. Okay. When we normalize it with the true value, we call it as relative error. If we represent it in terms of percentage, we call it as relative percentage error. So relative error is an easy term to compare the performances of different methodologies, different techniques, whereas absolute error will give you the magnitude of the error during a particular reference point. If reference point is not mentioned, absolute errors are quoted. If a reference or data point is referred to, then normally we give the relative error. Whichever has got lower relative error is more acceptable, as we have discussed in the first class regarding the accuracy of the measurement. So accuracy reveals the closeness of your value with the true value. So this is the same thing. There also we had discussed the same term, error, relative error. Now we will try to understand what are the different types of errors. Generally, if you go to any reference in the internet, you will see different classifications, because they have different references, sources. But when you go to any standard or basic textbooks in physics or chemistry, you will see that these are the three different general classes of errors. First one is the gross error. Then we have the systematic error, which have got a definite magnitude, as well as these will give you, these are called directional errors or determinate errors. They will have a particular direction. They will lead the final measured result to be on one particular side of the true value. So they are having some particular direction. Their magnitude is also almost predictable also. Once you try to understand carefully the systematic error and try to address those sources of errors, you will be able to almost get rid of these systematic errors. These are of different categories also. And random errors are those which are unexpected and which may cause the measured value to fluctuate on either side of the true value. So what will happen generally, natural tendency is that it will have values symmetrically on either side of the true value. That is the property of Gaussian distribution function that we apply for this random error analysis. Essentially, when we do the statistical analysis of data obtained during measurement, what we do is try to address the random errors, which we cannot get rid of completely. We can only minimize the random errors. There are systematic errors you can completely get rid of. Now we will see in detail the three different categories: gross, systematic, and random errors. So gross errors normally arise most of the time due to carelessness of the experimenter. It may so happen that the experimenter is not that can be comfortable on particular day of the experiment. So it may happen that the sample may get spilled from his or her hands, or maybe while weighing or transferring of the material from one container to the other container. Sometimes you are taking out the reading wrongly. Sometimes while writing down, some mistake may be committed by the experimenter, or while doing the calculation, mathematical calculation, you may commit mistake. Maybe you may forget the decimal point, or you may, like, instead of addition, you may be doing multiplication. Instead of say division, you do subtraction. Those small mistakes which are not anticipated from the other person, this will lead to gross errors. That how it will be visible, that we'll see in the coming slides. And if at all there is an inherent problem in the instrument which you could not rectify, say for example gas leakage is there, so you will see that a sudden change, a drastic change than expected is there, and finally you will land up in a wrong result, wrong portion than the expected one. Okay, so a few examples are given here. For example, if the room is not properly lit, it may so happen that the balance showed you some reading 76, but you read it as 70. Sometimes it may happen that digits 3 and 8, they may not be visibly separate. Sometimes if the balance display is not proper, the center horizontal line is not visible. So 0 and 8, there may be issues while noting down. So all sorts of errors come under the category of gross errors. A temperature of 25.8 degree, but while noting down, you might have wrongly noted down as 28.5 degree. Or sometimes it may so happen that the decimal was not visible for the reader. instead of 25.8, you may write 22.58. These all sorts of errors are under the category of gross errors. Okay, how it will be visible? If you plot, generally when you do any research, it is not the outcome of singular measurement. Keep in mind that if at all you find any new observation, you have to repeat it and just confirm that yes, whatever I report is not by fluke. I have done repeated measurements and affirmed that yes, whatever I see is something new, as we discussed in the very first slide in the first class. Okay. So when we do plot the repeated measurements in particular timeline, you will see that one of the data, so the one which is shown in orange or red font, red filled circle, you see that that is visibly away, visibly out of the other set of the data. So you call it as outlier. That means it is standing out from the rest of the data. So how you can mathematically verify that this data is not a part of the other set, it is visibly separate? That normally there are two such tests, Grubbs test and Dixon's test, mathematically to verify whether a particular data is outlier or is still part of the entire population. So Grubbs test, among the two tests, Grubbs test is the one which is recommended by ISO, International Standardization Organization, for testing for the outliers. If you find that one datum is visibly different from the other set of data, what you do, you apply this test and verify. If at all you find that it is an outlier, reject it and go ahead with the rest of the data. Okay. So this Grubbs test is the tool to verify one data which you suspect to be not a part of that particular set of measurements. So what we normally do in Grubbs test is take the difference between the suspected value and the mean of the value, take the ratio with the standard deviation. Keep in mind that when we do this Grubbs test to calculate the parameter, we call it as G. Grubbs, the first letter in that name, G, it is nothing but the ratio of the difference between the suspected and mean values to the standard deviation of the entire data set. Keep in mind that during this calculation for the mean and standard deviation, the suspect value is included during the calculation. Only after evaluation of the G value, if you find that the suspect value is an outlier, then only we take it out. Till the calculation, till the end of the calculation, suspect value is part of it. Only after proving it through that G test, you will see that if at all this calculated G value is greater than the value, the critical, we call it the values given on the right hand side in blue table, those are called the critical values of G. That is the acceptable upper limits of G for a particular number of data points. So for example, if you have 4 data points, the G value will be, the critical value of G will be 1.481. So if you calculate G value for a set of measurements, and if at all the calculated G value comes out to be greater than the tabulated value, then we say that the suspected one is standing out. It is an outlier. So we reject it. Then for further calculations, we recalculate the mean and standard deviation and represent the data in that manner. If at all the G value comes out to be less than the critical value, that is nothing but those given on the right hand side blue bordered table, then you include that value in the data set and go ahead with the further analysis. Okay. So what we do is we essentially calculate the G value from your set of measurements. If the calculated G value is greater than the tabulated G value, the datum is rejected as an outlier. If not, then we accept it. We accept that it is a part of this particular data set. Go ahead with that. Since the probability of occurrence of a particular data is equal on either higher or lower side, generally we do apply the G table for two-sided test. two-sided, that we will see in the next class. What is two-sided distribution, one-sided distribution. So types of distribution is the portion for the coming lecture. So now all of you carefully listen to this question and try to understand that one. And the table also I will show you. If a set of 4 measurements are shown here with the numerical values of the nitrite concentration in a particular sample. So just by seeing those data, one can easily decipher that the last data is visibly, noticeably lower than the other set. So whether should we keep it as a set part of this population or should we reject it? One cannot just like that reject it. We have to do the G test, Grubbs test, and okay. So what you have to do is the suspect value here will be 0.380. Average or the mean value one can easily calculate, and the standard deviation. The calculated G value comes out to be 1.432. Whereas if you see the table, compare the table for 4 number of data points, that is called the sample size. The tabulated G value or the critical G value is 1.481. Then our conclusion will be, inference of our conclusion will be, since the calculated G value 1.432 is less than 1.481, that is nothing but the critical G value for n is equal to 4 for data sets, the suspected data should be retained. Okay, that means it is not an outlier. But just by observing, we felt that it may be an outlier. But the mathematical evaluation through Grubbs test showed that it is not an outlier. When we do the Grubbs test and this test also, individual data points are tested one at a time. It is not that you have a collection of data, and it is individual data addressed one at a time. One by one only you do normally. At the same time, if you are rejecting an outlier, the sample size keeps coming down. That means the quality of data becomes poorer, because you see that when the number of repeated measurements are larger, the sample parameters will approximate the population parameters. So the idea is to increase the number of samples or the sample size without much time and energy and the instrument facilities and whatever requirements, maybe reagents or chemicals. Okay. Another way is in the Grubbs test, you have seen that you have to calculate mean and standard deviation, whereas there is much simpler way to do, that is called the Dickson test. Dickson's test, the other name is Q test. Here the Q value is calculated by taking the ratio of the differences between the suspect and nearest values to the largest and the smallest value difference. The difference between the largest and smallest value we call sometimes as the range of the data. Smallest to the largest, the range of the data. Okay. Here you will see that the Q factors, normally the Q values are fractions. The values are less than 1, whereas the G values were more than 1. As the sample size increase, the Q value keeps on decreasing in the tabulated values. Whereas in the previous one, you will see that as the sample size increases, the G value keeps on increasing. So these close observation of trends also you should keep in mind, so that being a researcher, you try to understand what is the trend of the data, so that later on, sometimes without doing experiment, you can predict in which direction it is moving, whether it is moving to the higher one or lower one. Whenever you see a data set, try to analyze in all its ways, in all 3 dimensions. You try to see what are the different parameters you obtain, so that your planning of future experiments will be well organized. So in the same question as the previous one of 4 data sets, if you apply the Q test, the Q critical value, the tabulated Q values are 0.829, and the calculated Q value is 0.7. Here again, the Q test also is satisfied. That means the parameter is retained. Okay, that parameter, that particular value is suspected value is part of that population. So you do inclusive procedure, go ahead with that parameter included, factor included. So you have understood the gross error, how to understand whether there is a gross error or not. If at all you find there is a gross error, you remove that result of that gross error, go ahead. If at all it is not a gross error, include it and go ahead. The second type of measurement errors is the systematic error. As I told in the beginning, these have got constant magnitude as well as constant sign. So these are determinate. These are predictable. If you interact with people, some people are predictable. In the next moment, if you tell something, how they will react. So their behavior is systematic. They are predictable. There are some people with time, with environment, if they change, they are not predictable, then they come under the category of random. Okay. Generally, people have random nature. Systematic measurement errors are observed if at all you rely upon some experimental device or a measuring device or an instrument. So if at all there is a change in the environment of the measurement, for example, the instrument is calibrated for working in a particular temperature and you are trying to use it in another set of conditions where the temperature is either on high side or on lower side, you will see there is a slight systematic change in the signal of the instrument. How you will ensure that we'll see. How you see that it is a systematic change. The total systematic error, normally we give the term bias of the measurement. How to assess the bias of the measurement, that we will see in the coming slides. Okay. Sometimes, for example, if you tighten the screw of a vernier or a screw gauge a bit more, you will see that instead of the zero position, slightly it is over screwed. So what will happen? Instead of the zero position, you will see that maybe one or two units ahead. So all the time, if a person is doing the same thing, same with the instrument, all the time the level of tightening of the screw will be almost similar. So all the time you will land up with same particular type of either increment in the reading or many times decrement. That constant either constant increment throughout or constant decrement throughout. Okay. So these are the different causes, normal causes of systematic errors. Maybe sometimes the instrument is, as I told you, instrument is calibrated for a particular working environment, working condition, but you change the environment, instrument behavior gets slightly modified, which you may not be noting down in the initial months, but ultimately that will be visible via like a constant shift in the final results. This shift we call as bias. Okay. Sometimes if you adopt a procedure which was not appropriate for a particular process, for example, precipitation, if you are not adding the sufficient amount of the reagent, you will see that all the time you get the weight of the precipitate lower than the expected. If you are constantly using the same wrong procedure, always you will end up in smaller, lower results all the time. Okay. Sometimes judgment of the measuring device by the person may also be wrong. So if a person is doing single-handedly the entire experiment, it will always have a particular bias in the final result, particular type of orientation, which is with respect to the original position. Okay. For example, if a person is reading the upper meniscus of a liquid instead of lower meniscus where it would have been, so always he will land up in smaller volumes of the measured values. So every time this will be there, finally what will happen? He will report a value of the volume smaller than that one. That also will be visible in the final measurements once you do some like calibration of the measuring device or you do analyze a reference material. Okay, these are all addressable. Once you have constant magnitude and constant direction, those can be addressed easily. And predictable behavior, predictability is there in the systematic error. Okay. So these are another causes. For example, indicators or chemicals if you choose wrongly. If the indicator is supposed to work in higher pH and you do the titration at lower pH, always you will see that the endpoints are not visible. That is one type of systematic error. Instrument, if it is not properly calibrated as required routinely, then the response curves may be different. Sometimes the instrument reading may not be visible, so that faulty reading due to the parallax error, maybe the environmental parameters such as pressure, temperature, that may affect the instrument performance. These all come under the category of systematic error. The environmental factors affect the measured result in systematic way as well as random way also. So how to differentiate between these two? Whenever the final result is oriented in particular direction, particular magnitude, then those causative factors we call as systematic contributors. If at all there is fluctuation in either side of the Gaussian curve, we call it as random error. Factor may be the same, the effect may be visible in different manners. So based on the outcome or the effect of the factors, we consider it as either systematic or random error. So environmental factors you will see on both systematic title as well as the random error. So systematic errors will not be revealed by statistical analysis. Those one has to be careful during the measurement steps. One can easily identify that finally and try to overcome the causative factors and come up with accurate results. So the basic processes and the methodology should be understood prior to carrying out any experiment. That is why wherever possible, if you are using a new instrument, read through the user manual of the instrument first. Then if at all there is a certificate of analysis of a particular material or a chemical or the reagent, read those ones. The material safety data sheet, whatever precautions you have to take while carrying out such experiments. If at all you are doing a precipitation, whether the required amount of the reagent you are adding to that reaction, the procedure should be well noted down, procedure should be well understood prior to carrying out your experiment. Okay. If at all you are proposing a new procedure, what you have to do is try to do it theoretically, estimate it. You have an empirical proposal, verify it if possible via computer programs, then only start experimenting. Do not start any experiment abruptly. Follow the procedures or guidelines given by your guide during such experiments. So these are the different categories of systematic errors. The different categories as we had discussed in the very first slide: instrumental, environmental, and observational errors. For all the three categories, examples are also given here. For example, on the topmost one, the instrumental one, there is an inherent background or the bias value in the balance. 2 milligram, even in the absence of any material, the balance is giving you some reading 2 milligram. So the beaker which you keep on the balance always will show a reading 2 milligram higher than the actual value. So one can correct it either by tearing the balance, or you can use the standard weighing box you can use and verify whether it is showing the actual values. So this process is called the calibration. Before proceeding any experiment, you see whether the instrument is properly calibrated. Then only you proceed for the measurements. Sometimes in the environment, some factors there may be poor visibility. Sometimes the environmental parameters contribute to the background or the baseline of the equipment. For example, in the Geiger counter, you try to monitor the radiation in the ambience. So if at all a mobile phone is kept nearby, you will see that the signal, radio frequency signal coming from the mobile phone is giving a background baseline. So you will see an elevated signal of radiation in the Geiger counter, which is not expected, but it is not due to the sample. It is due to the radio frequency coming from the mobile. So if you keep aside the mobile while doing the experiment, definitely you can get rid of that. Environmental factors you can get rid of easily. Maybe you keep the environment very clean so that the ambient things are not affecting your measurement. Maybe temperature, if the experiment is designed to do at lower temperature, follow it initially at that lower temperature only. Later on, if you want to improve or improvise yourself, you can do repeat at the alternate temperature. But when you are reproducing a literature, try to follow the procedure ditto as reported in the literature. Then only you will land up in the expected result. Later on, you do whatever modifications you propose during your research. Maybe you can change the temperature, pressure, or the room humidity. If at all dust is present, maybe the reaction is getting hindered. Sometimes the table is vibrating, so your balance may not be properly showing the reading. So all those things you have to take care. And the parallax error, all of us know very well that when you read a volume of a liquid, you have to see that the eye level and the level of the liquid in the measuring container is parallel to each other so that the reading is proper. Okay. And for transparent liquids, generally the convention is go for lower meniscus, and colored liquids go for the upper meniscus, as the lower meniscus may not be visible many a time. The same things which we had discussed in the previous one. These are the details and examples of the various causes of instrumental systematic errors. Okay. Why we discuss these things in detail? Because these are the ones you can have hold on and try to get rid of these errors so that your data will be more accurate, will be more close to the central circle, black circle, which we discussed during the discussion of accuracy and precision. Okay. Sometimes the instrument, whatever was calibrated in the manufacturer's side, if while transportation, maybe due to the change in the environment in the laboratories between the manufacturer side and our laboratory, there may be fluctuation. Sometimes the binding of the magnet may be slightly weaker. So finally, what will happen? There may be fluctuation in the reading. Okay. Sometimes friction, variation in friction due to the mechanical ball, maybe due to loss of ball bearing in mechanical measuring devices. You will see that there's a constant degradation of the final values. So that one can easily address the variation in the instrument signal. And misuse of the instrument. If the instrument is not properly utilized, you over tight the screw gauge, what will happen? The zero error will be there always. All the time you will land up in higher values. And the initial adjustment of the initial setting of the instrument, whatever is given in the user manual of the instrument, you have to read through thoroughly, follow the instructions, verify, re-verify that you have done properly. There may be guidelines or the procedure given to that one. Check it, then only apply for your set of measurements. Okay. So sometimes high resistance lead will give you wrong measurements of voltage and all. The same case, if at all there is an overloading of the instrument, for example, a voltmeter showing wrong data when it is connected to a very high resistance circuit, because it will land up in loading effect of the circuit. So if at all you have to measure the voltages, apply to the terminal having lower resistance circuit. So these are the simple steps one can take up so that systematic errors can be avoided completely. The environment of the measurement should be kept very good as possible, as clean as possible, so that you get the results reliable. If at all there is a recommended temperature for an instrument to operate on, you try to follow that one as far as possible. Maybe a few degree change in the temperature may be acceptable, but stick to that window wherever the recommended conditions are given for the instrument. Okay. And if at all there is a chance that the environment temperature may go up than the recommended one, what you can do is you can take care of that particular portion of the equipment either by making it immune to this type of effects. Maybe you can cover it or you can use shielding of the equipment so that the effects can be almost got rid of. So make sure that the equipment is properly utilized, and if at all your equipment is not able to perform properly, re-verify the connections and try to eliminate these disturbances if at all you find any such disturbances. So keep a watch of the calibration of the measuring device. If it is recommended to do the calibration once in a week, once in a month, once in a year, go through the manual and follow the instructions properly and keep a record, keep a logbook of those this calibration verification also. Only when required, redo the calibration. It is not advisable that all the time you redo the calibration for most of the instruments. If your instruments, they may recommend you to go for calibration of a particular parameter, only that parameter should be addressed prior to the experiment so that you can save your time also. Okay. In case there is a change in the instrument response due to the external or magnetic or electrostatic fields, then what you can do is you can provide a shield for the equipment so that your instrument is not getting affected by these fluctuations in the external field. Okay. And ultimately, even after taking care of all these things, you are not able to get rid of these errors. What you can do is calculate the effect of cumulative effect of such systematic errors, and you can apply the computed correction factors into that one. That is the last step of addressing systematic errors. Okay. The third category of errors is random errors. As I told you, they cause the measured result to fluctuate on either side, on higher side as well as lower side. So sometimes we are not able to predict their origin. So they are uncontrollable variables contributing to the final measurement result. So they are categorized into two, observational and environmental. Sometimes the experimenter or the observer is casual while doing. So instrument reading, sometimes he may forget to do the proper register of the instrument, the reading and calculations, minute mistakes in the calculation. If at all there is a big mistake or a blunder, that will be visible under gross error. That will be visibly separate from the rest of the data. Small mistakes which will you may have like your behavioral variations, small variations will not be visibly separate from the other set of data. That will cause the measured value to fluctuate on either side. Any continuous variable, as I told you, if the same person, same measuring device, same procedure is adopted, even after that, you will see that second or third reading will not always match exactly with the first reading. There is an inherent fluctuation or variation in natural variables. That is a property of Mother Nature. Natural variables keep on changing in time. So these random variables are associated with any measurement of continuous data. The only thing is that you can minimize the magnitude of random variation, but not eliminate it completely. The environmental factors, when we discuss the systematic errors, I told you that if at all the final result, this manifestation of the environmental variable is to cause the measured data on either side symmetrically, then we categorize it as random variation, otherwise systematic variation. Okay. So statistical analysis essentially addresses the random errors and try to reduce that one. And finally, what we represent along with the numerical value of the result, the fluctuation or the standard deviation. So the magnitude of the standard deviation will tell you about the ability of the instrument or the procedure or the method or the experimenter. So the reproducibility of the measurements will be revealed by the magnitude of the fluctuation, standard deviation. Ultimately, the efforts of all these statistical approach to research is to minimize that plus or minus part of your result. So keep in mind that we are only minimizing, we are not completely getting rid of that part. Major sources of random errors are listed here. Natural variation, that is bound to happen. One cannot avoid that. Something Mother Nature keeps on applying to all parameters. So real world experimental context, you will see that random errors are always associated with any measure. And if at all your instrument is not reliable for a particular measurement, maybe the instrumental calibration range is not appropriate for your instrument. You are trying to use it for that particular purpose. Again, it will have variation in the final result. Okay, and individual values also will keep on varying. Experimental conditions also you have to control, and random instrumental fluctuations also will lead to final variation in the result. Examples are effects of inertia or friction or vibration, or sometimes due to vibration, or sometimes you anticipate a vibration but the vibration is not present. So that also will lead to variation. Whatever we discussed regarding systematic and random errors, their comparison is compiled here in this slide. Systematic errors are determinate, random errors are indeterminate, and the systematic errors will lead to one-sided result in the final set of data. They will have a particular magnitude, whereas random errors are the other way. They will have both sides, two-sided data, and their magnitudes also are not predictable. Okay, and keep in mind that systematic errors cannot be addressed by doing repeated measurements, whereas random errors can be understood, estimated by repeated measurements. If one has to address the systematic errors, one can use calibration or the use of certified reference material, in short form CRM. Certified reference materials can be used to minimize the systematic errors. And systematic errors lead to bias. Random errors, we can only reduce the random errors. They are represented as repeatability or reproducibility of the final results. So if you want to reduce the systematic error, what you have to do is you have to understand, plan the experiment, anticipate wherever problem areas are there. Try to start to address those problems before you start your experiments. And that is the careful design of your experiment, use of appropriate standard, and periodic checking of the instrument performance, and standard reference materials, and wherever possible, cross-check your results with the alternate procedures also. Okay. And you can participate in inter-laboratory or proficiency testing and evaluate yourself whether your values are as per expectations or not. Okay. The random errors, one can try to reduce the random errors. So for that, we can do repeated measurements or increase the number of samples, or the sample aliquot size also you can increase, so that it will be a better representation of the population factors. And the environmental factors one can try to control by taking care of the factors such as pressure, temperature, or dust or humidity, vibration. So all those factors can be taken care to the best possible. This way we can try to minimize the random errors. Here are a few questions for you to try to attempt after today's discussion. We leave at this point for the discussion. All of you can note down these questions and come with the answers in the next class. Then now we will go for the chat box and see if at all there is any discussion required in the day's lecture. If anybody wants any clarification, you may please write down in the chat box, as we do normally. In the meantime, I will summarize today's discussion. We had a recapitulation of the previous 3 lectures. Today we discussed various types of errors, gross, systematic and random errors, the causes, the ways to tackle this, different categories of errors. Next day, we will see the distribution of data, different types of distribution of variables, continuous variables distribution. Anybody wants any clarification? You may please write down. We will check in the chat box. Huh? Till now, I have not seen any questions. If there is no doubt, we will wind up. If at all you want any discussion via mail, you may do so. Otherwise, we have completed 4 lectures. Next Monday, we will have the 5th one. You can go through this. As I understand, all of you may be getting this recorded videos also. Please go through during the weekend, and if you require any help from my side, come with those for the next class, Monday 4 to 5. Last 5 minutes we dedicate for such discussion. If there is no clarification required, we will wind up for the day. Okay.